pleasure to be here, and fenestration is a subject very near and dear to my heart. It's a topic that I have been really working hard for the last decade plus to move the industry forward here in North America. So I'm delighted to host this event today and bring together a really quite a spectacular roundup of presenters to see how we can move the needle forward here in North America's fenestration market. Quick review of the schedule. This is available on our website for those who would like to check in, but I will be periodically referencing this. First session will look specifically at metrics and certifications, followed by a moderated panel discussion, which I will lead. For questions, we won't be taking questions directly from the audience, but we will look at the chat. So if you do have burning questions, we will try and include some of them from the chat discussion. We'll follow this by a break. Everybody, encourage you to get up, move around. And then the afternoon session will really dig into policies that can really drive high performance fenestration production forward here in US specifically, but in North America in general. So that's the schedule. The agenda really is a big and hairy question, not only just really helping to share what the metrics are and the certification processes are for passive house windows, but really the bigger question we're trying to ask here today is, how do we drive both production and demand? Because we know very clearly, and from hard-won personal experience, these two have to work in tandem. And then secondly, really, what are the policies that we can help promote to move windows forward? Because we have seen this is where this is a driver, it's an engine that we need to leverage a little bit better. And hopefully today we can help contribute to that discussion. And just to establish some baseline terms, for those of you in the window industry, you will probably be familiar with a lot of these, but for those new to the discussion, I want to just establish a few metrics and terms so that you at least get a sense of what we're talking about when we convert to jargon, window fenestration jargon. Really, the first challenge that the overarching challenge that we are really tackling today stems from this basic need in the passive house community for granular data. On the left, we've got what we typically require for code compliance, a U window value. Oftentimes, sometimes, we also need the solar heat gain coefficient in the U glass. But essentially, this is the landscape that we have all been working in, and are still required to work in. And this is the data we get. For passive house, it gets clearly a lot more complicated. And I'm not going to go into the nuances of all of this, but just want to show you the difference in the amount of data that passive house requires for window modeling. And then just a quick illustration of some metrics that are commonly used in the NFRC rating protocol and the passive house protocol, just so that you have a basic understanding of the terminology and the metrics. On the left here, you'll see U frame, U edge, and U center of glass. And below, area of frame, area of edge, and area of center of glass. And then on the right here for passive house, things get shifted a little bit. And you'll see U frame, which is common to both. Size spacer, this is where there's a little deviation from U edge. and U center of glass is the same. You then get area of frame and area of glass, and then there's an additional metric here, linear edge of glass. So just to show that and provide some basic terms there for you, we will share these as a PDF afterwards, and all of this is available on the recording. And then to establish some metric conversions, we're working in different units, which adds another layer of complexity. The European protocol and the Passive House Institute works primarily in SI units, although they have been kind enough to translate the PHPP into IP units for the US market. We here in North America primarily are still using the inch-pound units system. And just to sort of get a baseline structure here, these are the same metrics. So the blue ones are in the BTU per hour square foot Fahrenheit. The red ones are in metric, watts per meter squared Kelvin. And so just to establish, so you have a rough frame of reference here for everybody. And just to give you in the metric system, 1.2 is the equivalent of the warm and humid climate requirement for a window in Passive House, which is equivalent to a 0.21 in BTU hour square foot Fahrenheit, or R5. For those of us like myself, architects, we sort of think in R values rather than U values. And then at the other end of the scale, 0.4 watts per meter squared Kelvin, which is the Arctic climate requirement for a Passive House certified window. It is equivalent to 0.07 BTU hours per square foot, or R14. So just to set those metrics so everybody has a frame of reference, and we can do rough basic order of magnitude conversions. So with that, I would like to begin by introducing you to our first presenter, Adrian Maskadowitz. Adrian joins us from Germany. His house, we're working remotely like everybody these days. Adrian is with the Passive House Institute and is their lead on fenestration and component certification. I've had the pleasure of working with Adrian for quite a while. We, in 2015, did a tour around the US. I dragged him to places all over, including Wisconsin, for the Wood Window and Door conference back in 2015. And it's a pleasure for me to welcome him here today to share a little bit more about how the Passive House Institute certifies products and the processes and metrics. So Adrian, I'll hand that over to you now. Thank you.
Yeah, thank you very much. I'm really happy to be here today. I just would like to give you a quick overview of what we do in the Passive House Institute. What are the targets, and I would like to split my presentation into the past, the present, and the future. And sorry. So when the first Passive House was built in Darmstadt, when Wolfgang Feist planned it, there was no component available at that time, right? So there was no triple pane glass, there was no warm edge spacer, there was no insulated frame design. So they had to come up with an idea how to get to that levels they needed, also in terms of comfort, efficiency, and hygiene. So they had some custom-made prototypes, and they end up in getting to quite good performance. So what we're doing, they were actually buying some EV68 profiles, so solid timber frames, which were typical at that time in the beginning of the 90s. And they were covering them in insulation, so made of carbon dioxide foamed polyurethane, and they get to quite a good level, so which can be considered as a certifiable component nowadays. But you have to consider they still had to use aluminum spaces, so they had a kind of high thermal bridge for the glazing edge bond. So they were trying to mitigate that thermal bridge by having a very high glass inset. And today it's still working, right? The house is still there. So those of you who have ever attended a Passive House conference might have had the chance to visit that place. And after 25 years, we were measuring the performance again. And even today, the average thermal properties remained close to the same level with one exception here, right? So there are no more excuses in not developing passive house suitable components, right? Because they also made it 30 years ago. So just a brief introduction, what is the Passive House Institute? So the very first Passive House you can see in the background. And Wolfgang, he was so convinced of that principles of that design that he developed the concept more and wanted to show that it works in practice. So he founded the Institute in 1996. So we got a bunch of passive houses built worldwide. We have currently 70 employees at the Institute, specialized in different fields. You can see a quick overview here, and what we're talking about today is merely the component certification and consultancy. And now I'm getting over to the present. So maybe some of you have seen that before. We have a component database you can find in our homepage, passivehouse.com. And we have basically 15 main categories with a lot of subcategories. Today we're talking about fenestration and transparent components, so I'm not going to highlight the HVAC opaque components and domestic hot water. But just to give you a quick overview of what we've done within the last years. So the whole certification, component certification process started in the year 2000, and we had the first glass and window certified in the year 2005. And from that on, with the manufacturers together with the industry, with the Passive House planners, we introduced more and more categories, more and more design guidelines, and we're implementing more and more components, right? So this is just an excerpt for the transparent components, and we're trying to enhance that over the time, and also to update and improve the criteria. So what you can see here is when we filter the component database for transparent components, you can see that we have approximately 70% of available components. They are based in Europe. We have approximately 20% in China, and the rest are, yeah, we've got only a few in North America. And so there's still a lack of local available components, right? And this is something we could maybe change. So we have more than 1,000 valid certified components worldwide. And if we look at that for the transparent components, it's approximately 400 certified transparent components, where about 300 are windows. And I just would like to go quickly to the certification criteria. So this is just a brief introduction on a very rough level, just for you to know what we do. We have certification lines for different climate zones. So that means the certification requirements might differ. So what you can see here on this table would be one of the criteria, which is the heat transfer coefficients. What you can see here is the UW values and UW installed values for the windows in SI and IP units. And what we do here, and Bronwyn already indicated that, is we look at these specific components, right? Because Passive House is all about helping the planners to have a flexible system, which allows us to make some modifications to try to get to the optimum for each building. Also to play around a little bit with the Passive House planning package to get better results. So therefore, we have separate certification lines for the glazing, for the spacer, and for the window frames, right? So therefore, we have a predefined quality for the glass units whenever we certify a window frame, because we don't want a high performance glass to compensate a very poor performing frame. So we would like to give the architects and planners a certain freedom. But mainly the simulations, what we do are based on the EN 10077. There's a mistake, it's 77, not 10,007, and the ISO 15099. But we also have some slightly deviations, especially we consider certain punctual thermal bridges. For example, when we look at curtain walls, we look at the glass support, we look at the fasteners for the pressure plates, things like that. And we also look at the installation. So if you translate that into values, you can see the different requirements here. These are referring to the installed window component, so including the thermal bridge of the installation. Another criteria is always the comfort. So when we look at temperature asymmetry, when we look at cold downdrafts, when we look at vertical temperature gradients, we try to limit the maximum difference of operative temperatures. And by doing that, I don't want to dive very deep into that right now, but we can get, for certain climates, we can get different requirements. So the colder it gets, the lower the U value needs to be. But other criteria might lead to lower U values too. That can be, for example, hygiene. So water, we need to limit the water activity on surfaces in order to prevent mold growth or condensate. And also efficiency and cost effectiveness might lead to different criteria, right? So it's always a mix of different things we look at when we look at the requirements, and we try to come out with a value that can represent that. Okay, don't want to spend too much time on that. You can read that out on the Passipedia or on the certification criteria if you're interested in that. So another thing that I mentioned is that in contrary to the standards of coded codes, we consider the installation thermal bridges, right? So for all the components, they need to achieve the requirements for 3 wall assemblies, where the EIFS is mandatory. So you can see an example here. So for a window installation in front of a wall, you can see the corresponding values here. We're also looking in particular for the spaces and for the whole glazing edge bond. So that is another topic where I think Helen is going to spend some words later on. So this is another thing where we slightly have differences because we've been talking to the industry a lot within the last years, and especially for IGUs with higher thermal stress, for larger panes. It turned out that we need thicker secondary sealants than stated in the codes. So we have like depending on the geometry, we look at different sealant thicknesses and allow different secondary ceilings. And when you look at our certificates, you can see an excerpt for one spacer here on the right-hand side. You can see that the thermal bridges of the glazing edge bond, they differ from curtain walls to window frames and also from the glass setup, right? So we have a kind of dynamic approach here. Okay, so the essentials, just to give you a quick summary of what we look at for windows, we try to get, and this is something which all windows have in common, no matter if these are vinyl windows, aluminum windows, or timber integral windows or whatever. They all have a low visible height. They have a high construction depth, which also gives us a high thermal resistance. We somehow try to mitigate the thermal bridge of the glazing edge bond, whether by having high performance components or increasing the glass inset. Aesthetic design is also very important, and we always try to have, and this is what you can see on the left-hand top, that the manufacturers try to have also like an installation concept, which also includes the shading, right? So that we don't have the gap on site between different craftsman territories, right? So facade, installation, shading, yeah. So what we're looking right now, and now just 2 more slides, would be what is the future all about, right? And we are merely looking at innovative concepts, right? Concepts that are adaptable to various climates. So having different glass design, maybe solar protective glazing, but actually the same frame structure. One example could be first all climate window concept from Hebei or in Sundar. But we're also looking at things that, or components that help us to have this synergistic combination that can be with the facade structure, that can be with light transmittance, implementation of HVAC components. We got the first components which have also like a combination to the HVAC. And we're also looking like at would like to look more into special solutions like barrier-free constructions and so on, and cost effectiveness, right? So on the very left-hand side, you can see the first window design from 1991. In the middle, you can see like what passive house windows look like nowadays, and now we're trying to get to the next step. Okay. Another important thing is the curtain wall design, because that became more tricky over the years. I mentioned that before. We have a very high thermal bridge of the glazing edge bond, because contrary to the windows, we have now 6 or 8 millimeters secondary sealing thicknesses. We have very limited options to reduce the heat flow inside of a rebate. We need to consider the fasteners, glass support, everything else, installation and airtightness concept. And what we would like to see would be the first manufacturers that also include the shading system concepts, right? So this is what we're looking for. And if you're interested in working with us, feel very free to get in contact with us. Components at passive.de. And for more information, you can visit Passipedia or our homepage. That's mainly it. Thank you.
Thank you so much, Adrian. And so next up, we are going to go to Helen Sanders, who joins us from Technoform and is also a board member at the Facade Tectonics Institute. Helen, I'm really excited to have you here to really look at some more kind of granular issues, challenges with edge spacers as your current area of expertise, but also just looking at the bigger picture of where NFRC ratings and passive house ratings have some sort of challenges and some potential conflicts that we can hopefully look and see how we can resolve. So thank you, Helen. I'm going to hand this over to you. Get going.
Great, thank you. Really appreciate it. Can you see my screen well?
Yep. Looks
okay, great. Thank you. I appreciate the opportunity to be here and to follow Adrian. So I'm going to take a dive into the edge of glass and talk a little bit about the trade-offs or the considerations that we really need to make or bear in mind when we're looking at thermal performance. So the edge of glass is the key to the durability and the service life of the insulating glass unit. And as Adrian just talked about, is also key to the structural performance, which is why as you get to larger commercial glazing, you need to put a lot more sealant behind it. And also the type of sealant makes a difference to the structural performance, and the choice of sealant is different in, say, curtain wall and high structural requirements for regular fenestration than it is for, say, residential fenestration. So we need to consider both the thermal performance and choices in thermal performance, the impact that they have on the service life of the insulating glass unit. So I'm going to start by just doing a very quick overview of the edge of glass durability. Then I'm going to talk about the thermal performance and then bring it all together in the context of passive house. So little graphic here that shows what you might call the state of the insulating glass unit over its expected service life. And you can expect the service life of 25 or more years if the edge bond is carefully designed and it's well manufactured and installed well. But you can end up with shorter service lifetimes if you don't have a design that is application specific. So you use, say, a residential style unit in a commercial application. You have low quality or less material, like Adrian just talked about. You don't use enough secondary sealant, or use the incorrect spacer for the application. If you're not designing your insulating glass units to take into consideration the climate zones that it's going to experience, if you have poor workmanship, of course, and of course, poor installation. So I'm going to talk about material choice and design and application specific edge bonds. So before we start that, just a quick look at the geometry of a typical edge bond in insulating glass. This is what we call a typical dual seal system. Dual seal meaning there are two seals. One primary seal, which as you see here is PIB or polyisobutylene. It's chewing gum basically, but don't eat it because it's not food grade. You have a spacer. In this case, I'm showing a box spacer. Typically, you fill that with desiccant. That's to take up any moisture that comes into the unit during its lifetime. And when that desiccant's used up, basically you start to get condensation and your unit fails. So the desiccant is also very important to the service life. And then you have a secondary sealant, which is part of that dual seal system. The secondary sealant is there typically for structural reasons. It can also help with moisture vapor and gas transmission reduction, but not all the time. It depends on the sealant, as we'll talk about later. The key here is that the system, this edge bond system is a system. It's not a collection of components that you can go change out without potential consequence to the lifetime. So you really should think about this as a system and not something that you can just say, oh, I'm going to swap spacer A for spacer B or sealant A for sealant B. It doesn't work like that. The choices that you make here are really important for determining the service life. And there are some key durability factors. The material choice, and that is the sealant, that's the spacer, the amount of desiccant you use, Critically, the sealant path length and contact width that you have to the glass, the number of penetrations or how you seal those penetrations in that primary seal. And then, as I mentioned before, the ability or the importance to design for climate loads. If you imagine you have a sealed insulating glass unit so that you've got a cavity filled with gas and it's sealed. So when it gets hot during the summer or the height of the summer's day, the pressure in that in the side, that cavity will go up, and that will put a stress on the insulating glass unit. The bigger the unit, the more likely, the more flexible the glass is, and the more likely the glass will bow out to take up that pressure. But smaller, stiffer units or multi-cavity units, triple panes, for example, they are more stiff, and that pressure is typically taken up by the extension of the edge seal, which can increase the moisture vapor transmission or the gas loss. And so smaller, stiffer units, we have to be very careful to change or make sure that the edge seal design is appropriate to the stress it's going to see. So devil's in the details of the edge seal. So let's take a look at the North American commercial fenestration, typical construction. In contrast to Europe, where I would say, with the exception of structural glazing, curtain wall applications, the majority of commercial insulating glass uses a polysulfide or a polyurethane secondary seal. The majority of all commercial insulating glass has a silicone secondary seal in North America. So that's a big difference between North America and Europe. And that has driven different spacer usage in North America and Europe. So typically, commercial glazing in the US has a silicone secondary seal. And the reason for that is because it has excellent structural performance. It has very high UV resistance. It has great water resistance. So if you put it in a badly wept frame, it will do better than a polyurethane or a polysulfide system, for example. It has high temperature performance, so great for North American applications. But on the downside, it's actually a very bad vapor barrier. So if you think about your shower, silicone is great for resisting liquid water, but it breathes. It allows moisture vapor through. It also lets argon through. So what that means is that when you have silicone as a secondary seal, you rely on that primary seal, the PIB and the spacer, to be the only moisture vapor and gas barrier. So that's what you have to rely on. And for this reason, when you have silicone secondary seal, the spacer that you use should have a solid metal vapor and gas barrier in its construction. So that means aluminum box spacer, which is not great for passive house because it's not warm edge. Stainless steel box spacer, really basic warm edge. Or a plastic hybrid stainless steel, which basically replaces a lot of the metal with plastic, and it has plastic bridging the top of the spacer, but it has very thin stainless steel around the sides and the back, which gives you a very, very good moisture vapor barrier. So that's why in North American construction, IG construction, you end up with these kind of spacer systems because of the ubiquity of silicone as the secondary seal. And you can't really change that out in structural glazing because that's a requirement. You have to have silicone in structural glazing. And typically the height of the silicone, minimum 4.5, typically it's more like 6 millimeters or 1/4 of an inch on the back of that spacer. So before I go on to thermal performance, I just want to take a little trip into triple pane because it's ubiquitous in passive house applications, as you could see from the numbers that Bronwyn and Daniel were talking about. you basically need a triple pane in most climate zones. The challenge with going from a double pane to a triple pane are really twofold. From a design perspective, as I mentioned before, because you've doubled the cavity dimension, you end up with increasing the edge seal stress for a given climate condition. So for a given high temperature or wind load, you're going to have a much higher edge seal stress on a triple pane than a double pane, everything else being equal. It requires you do an analysis and adjust the edge bond design for smaller windows, because those are the ones that are stiffer and more likely to have the pressure taken up by the edge seal. Also, it's harder to get to ensure good workmanship, because as you can see from this diagram, 2 of the 4 seals are now not inspectable. So it's you have to make sure that you have very good process control and repeatability. So there's a question here, and there's really no data in the marketplace at this point, but there's a question there: should we expect a shorter service life? And that, I think, we have to think about and focus on process control and design, edge bond design for, as I say, small stiff units to ensure against that. So let's talk a little bit about thermal performance. And what I want to do is compare North American with Europe. Bronwyn and Daniel did a little bit of this, but I want to be really sure that when that everyone is aware that the U factor that we calculate in North America through the NFRC 100 standard is different to the ISO 10077 that Daniel mentioned. Apparently physics is different across the Atlantic, but joking aside, there are different assumptions used in those calculation methods. So even if you translate BTU units, IP units into SI units, and you use the 2 different approaches, the same window will have a different U factor value depending on the approach. So we have to be very careful about not comparing, not taking a European or a passive house U factor requirement in SI units and turning it to BTUs, and then comparing it to an NFRC rated window. You can't do that because the calculation method is different. So that's one of the things to bear in mind. The other thing is, as Bronwyn mentioned, in North America, we really only rate the assembly, whereas in Europe and the passive house standard, on which, and that's based on the European methodology, U factors of the frame, the edge, and the center of glass are considered independently of each other. And frame manufacturers, for example, can give you a U factor of the frame because that's how they're measured. Whereas in the US, nobody gives you a frame U factor because it's not required, because we care in North America, we just care about the assembly. So there are some pros and cons of each of these systems, which I'm going to point out. We just need to be aware of some unintended consequences. So on the pro side for the North American approach, it allows for several strategies to achieve the overall performance. And it allows you to manage durability risk in the insulating glass unit. So you can have improve the center of glass and not do so much at the frame, or vice versa. The downside of that is that it creates an unbalanced, it can create unbalanced designs where the center of glass is used a lot to drive the overall performance, and you end up having not so great edge of glass and frame, and you end up having condensation issues. So that's one of the downsides of the North American approach. Now on the, if we look at the European approach, you end up with a much more balanced window design, because you're taking care of the frame thermal performance, the edge of glass, and the center simultaneously. On the downside though, because you are looking at these independently, you can lose sight of the impact of incremental improvements on, say, the edge of glass, which is the smallest factor in the overall U factor, you can lose sight of the improvements, the impact of those improvements on the overall U factor. And you could end up saying, okay, I've got a 10% improvement in my edge of glass. Oh, that's great. But I may have done some things like reduce sealant or change the spacer that may have impacted, potentially have a long-term impact on service life. But when we look at the overall U factor of the fenestration, hardly moves the needle. So just need to be careful of not just looking at the detail, but then taking a step back and looking at the overall performance, just to make sure that we're having an appropriate balance between those thermal performance and service life. And just a quick refresh on what Bronwyn told us. The thermal performance calculation in Europe, it's the U factor of the frame by times its area, plus the psi value, which is the linear thermal transmittance of the edge of glass and frame interface, multiplied by the interface length, added to the U factor of the center of glass by times its multiplied by its area. That's how we do it in Europe. And the next speaker is going to talk about how you do that calculation using the North American tools that we have. But what I want to do here is take a dive into the psi values, because that is something that we're not used to hearing about in North America. So spacer manufacturers in Europe are able to give you a table like this that I'm showing you. This is an example of a plastic hybrid stainless steel. It shows you the psi value of a dual pane and a triple pane in 4 different generic framing systems, because the psi value not just is determined by the spacer, but it's also determined by the frame itself and the interface with the frame. So psi value is determined by the frame, the sealant height, the bite, and also is obviously a function of the double or triple glazing. Then there's this value called lambda equivalent, which is basically the effective conductivity of the spacer. It's not the same as NFRC's K effective, so don't get them confused. This is just related to the spacer, not the complete edge seal. So just quickly here, some data. Sealant height matters. This shows you how the psi value can change with the amount of sealant. Frame bite matters. If you bury the edge further into the frame, you get a better psi value. And we'll note here is increasing a frame bite has much less impact on IG durability than reducing the sealant height. How much difference does it make on the U factor and your choice of warm edge spacer? So I'm going to give you an example here. This is using a US manufacturer's very high performance frame, very similar to European high performance windows. In this case, I'm just using a dual pane as an example with an appropriate sealant depth. I'm using 4 different spacers to compare: a stainless steel box spacer, a plastic hybrid stainless steel spacer that, as I mentioned, is plastic, but it has stainless steel around the sides and back. A full plastic box spacer that has a metallized foil around the back, not a metal, and then a foam spacer that also has a metallized foil as a vapor barrier. Now, this is the example, these examples, this is the results. This is the window U factor in NFRC U factor in the IP and SI units. I've identified the vapor barrier. As you remember, solid metal is what you use with silicone. And this is the spacer lambda equivalent, which is like their effective conductivity. You see, effective conductivity goes down, but what you notice, there's quite minor changes in window U factor. And I'm giving them out to 3 significant figures. Normally, you'd only quote them to 2, so it's really in the rounding. Here's just an example of a plastic hybrid stainless steel spacer versus an all plastic box spacer. The difference in the psi values across for different window types is somewhere between 009 and 013. If we translate that to the effect on a whole window U factor, we're looking at about 0.05 in SI units, which is about around the rounding error, maybe a point. It has less impact as you make your window larger, and it has more impact if you have better frames or you go to if you go to better frames. So just quickly on passive house considerations, Daniel just talked about this. If you go to the Arctic category for the passive house certified spacer products, you will find that they're all 100% non-metal. They all have plastic metallized foils as a vapor barrier. They're typically qualified to European seal standards with polysulfide and polyurethane, not silicone. And they're typically used for residential windows, not aluminum commercial systems. So you really need, in order to get to these levels of performance, you have to take the metal out, which when you use silicone is typically not a good thing to do. So really what you want to do is have the best combination is the plastic hybrid stainless steel, because it has low conductivity, but it also has good durability with silicone. So conclusion, passive house certified spacer, really not guaranteed drop-ins into North American edge bond. You remember that silicone issue. Vapor barrier is key to durability. Hybrid spacer is a good combination of durability and thermal performance. And the psi value depends on many different factors. Sealant height and effective conductivity of the spacer significantly influences durability, whereas the frame and the edge bite don't. And you can achieve a similar performance with the hybrid compared to an all plastic spacer if you adjust all other factors. So the frame, the edge bite, and the sealant height. So with that, I'm a little over time there, but lots of information, just devil's in the details.
Wonderful. Thank you, Helen. And always interesting to go deep into the weeds and a very edgy presentation. So next up will be Daniel Halland. Daniel joins us from north of the border up in Canada. Daniel works at RDH Building Sciences and is their technical lead on thermal simulation. I'm really excited to hear Daniel's presentation, because I think Daniel will be seeing and presenting a little bit of a bridge protocol, a research report and protocol that he has developed in conjunction with Peel Passive House. And it's a really interesting process that I'm excited about, and I'm looking forward to hearing a little bit more from Daniel about that. So Daniel, go ahead. Let's dig in.
Thank you for the introduction there, Bronwyn. And yes, so today, my goal here with the talk is really to highlight what a label isn't telling you. And part of this is, as Bronwyn mentioned, a procedure that was developed to help bridge that gap that Adrian and Helen mentioned, that there are differences between the way that we model our window products and window systems, more appropriately, to the Passive House Energy Modeling Standard and for labeling purposes in North America. So there are differences. The good news is there is a procedure to bridge that gap, and we'll talk about that today. Actually, before I move on, I do want to acknowledge again the partners who developed this procedure, Peel Passive House, who has actually joined us on the call here. So the Canadians are among you. They're scattered throughout the participant list today. So they were obviously a huge part of this, did quite a bit of the work involved in developing this procedure, and obviously Passive House Institute as well. And the work was funded by BC Housing and administered through FenBC. All right, I mean, it's a short talk, so it's kind of weird to have learning objectives, but nevertheless, at a high level, what we're hoping to do here is to really understand how the Passive House standards and their approach to Windows has driven performance and development of high performance Windows systems. I'll say that it's not an accident that there's this pervasive understanding that, or this perception that Passive House windows are high performing thermally. It's not an accident, and we'll look at a few reasons why. Remembering, again, we're kind of hammering this home, beating a dead horse, so to speak, in terms of that they are different and they can't directly be compared. So we'll look at that again. And then finally, just recalling that there is a procedure out there that uses therm. So for anyone who likes those red circles of doom, you can still use therm and come up with design values for use in the Passive House standard. So what makes a window high performance? There are some things that North American manufacturers get. It's high performance framing, whether it's low conductivity frame materials like vinyl and fiberglass, or highly insulated frames, or frames with large thermal breaks, or wood, etc. So we kind of understand that aspect of it. It's high performance glazing and spacers. It's that ubiquitous triple glazed window on a Passive House project. It's high performance spacers that Helen went to quite a bit of detail on. But windows don't float in space. And this is one of the major differences between the sort of North American approach at looking at windows versus what Passive House has forced manufacturers and teams to look at in Europe. So one of the differences here is, windows are designed for installation. Windows do go in a wall, or presumably it would. And what that means is that when you're looking at the pieces of your frame, you might start to wonder, do I need it to be this sort of aesthetic component on the outside of my frame, or are we actually going to flash all over that? So I actually don't need those pieces. How am I going to flash? I'll say, I'm a building enclosure engineer first, so I really worry about water. Every day, all day long. And so we do need to make sure that we don't have leaks into our buildings, and having window systems which are designed to accommodate that in a way that doesn't increase heat loss around the perimeter is incredibly important. Now, if the focus of today's talk was looking at numbers, that would make me extremely happy, but perhaps thankfully I haven't included those. But in terms of the scale of magnitude of this particular problem, if you do not install your window properly, you can take the performance of your window, from about a triple glazed performance down to a double glazed performance value. So it's a really meaningful problem that some manufacturers out there are actually trying to solve. We design our windows for shading. Windows are unique in that they not only separate inside from outside, but they also allow for some passive solar heat gains. And knowing when we need those, when we don't need them, and making sure that we have that control is critical. And perhaps somewhat obviously, that they're designed for review. Passive House projects don't just have little porthole windows. They have windows where they need them, or where they're desired, and they're big, or they can be small, and they can be targeted for areas where people actually are going to go and look out of the window as opposed to being located at your feet. So at the end of the day, a high performance window is a window that's been designed with and for a purpose. So it is not just high performance frame, glazing, edge, and spacer, but it is also designed for installation, shading, view, ventilation, solar gains, and so much more. And none of these extra things are on a label. So when you are evaluating your windows purely in the context of comparing option A versus option B, there is a lot about a high performance window that you are potentially missing, which leads us to Passive House. One of the fundamental, so these are, there are some fundamental Passive House principles that go into what is known as a Passive House design. I think locally in markets where we all live in igloos. These are things which are becoming a lot more commonplace. So things like airtight enclosures, heat recovery ventilators, thermal bridge free design, high insulation values, these are all becoming more and more common. But an important parameter, since the beginning of Passive House has been design of windows and Passive House windows. The available market and the types of projects that are seeing this type of problem we're trying to go and design for windows the purpose goes from single family homes to mid-rise all the way to some of the tallest buildings that we have in our cities. So really it's not just a punched window problem. The Passive House principles, designing for a purpose, designing for thermal bridge free design is something which we are seeing across every size of project, from hospitals to fire stations to pools, etc. But we're talking about North America. So what does that mean? So if we're looking at the market that we have in place, historically there's been relatively few North American products which are designed with the right inputs and data and performance values for Passive House projects. Based on an earlier survey that was conducted by the Passive House Network, there's definitely a preference in North America to look for local options. So there is an opportunity for manufacturers to market their products here. But U value, performance data, that is one of the major gaps. How do we compare North American products which have had tested reliable U values in the context of windows floating in space, but they've had tested and simulated data for many, many years. It's something which the industry is quite familiar with, has a lot of expertise, and in the scope of the program is done extremely accurately. And so we've got a whole bunch of different parameters. How do we navigate that? So this is really mostly for reference for people who look back at this slide, but they're fundamentally the difference in a Passive House designed window and a North American designed window does go down to some of those design standards that are referenced. So NFRC 100 for most people on the call is probably a standard number that you've heard of and are familiar with. And the comparable standards are ISO 10077 and then a variety of others. It's a relatively minor point for this talk, but there are also some Passive House Institute specific rules that the reference procedure tries to cover as well. So why does this matter? They're being simulated. Both standards have been used to predict energy model or energy loss through buildings. So why should I care? So there are a couple of reasons. One is very fundamental. You just don't have the right inputs to put into the energy modeling tool, which is one problem that you could perhaps solve through simple math. But the different algorithms and rules also lead to different answers. And so here's one example that's relatively important in a window performance, looking at center of glass U values. So this shows two lines. The first line in dark blue are simulated U values according to the NFRC standard with a temperature close to 0 degrees Fahrenheit at different gap widths. And then the pink dashed line is according to the ISO standard, also simulated at a different temperature, which is 0 degrees Celsius or 32 degrees Fahrenheit. And what is relatively apparent is that if you were the manufacturer and you're designing to this, your local standard, well, what gap size are you going to use? In North America, that gap size is traditionally on the order of 1/2 inch. And in Europe, those gap sizes have tended to be larger, closer to 5/8 of an inch or in that magnitude. So when you look, or when teams look at products designed in Europe for the Passive House standard or to the European standards, one very common and obvious difference is going to be the gap size and that IGU. And if you're looking at the difference in U value on the left there, that can be very, very significant in your overall product calculation. And then fundamentally, if you're on a project team, you're looking at test reports and trying to understand, well, what number do I use? How do I use it? The labeling standards and approaches are incredibly different. If we look on the left with a typical NFRC label for a window product, this is, it typically reports just these summary metrics. It is a U value, a single U value for the overall product, inclusive of glass, edge, and frame. It's at a standard size, and that is the number that's used. That goes into the energy model. It's applied to no matter what the size is on that project, and that's all the design team has when they're evaluating that window product, unless they have access to a more detailed report or ask the simulator to run additional calculations. And it's somewhat of a bit of an industry dirty secret, but we all know we all know that this is not the most accurate way of estimating annual energy use. It isn't. We all know this. And yet in North America, the assumption is, well, that's not really the purpose of this labeling, right? When I talk about it being designed for a purpose, the NFRC approach is designed for a purpose and its comparisons. And it's not, unfortunately, for estimating or modeling building energy use in a more accurate way. Comparatively, if we take a look at the way that a passive house certificate breaks out that information, it simply provides more data that allows project teams to literally model every single window on that project. And so for projects that are kind of in those 60-story range, that is an enormous task for the passive house planning package or the individual who's in charge of that model. Nevertheless, yes, they do in fact model every single window and every single orientation to get a specific installed U value for every single window on the job, which does allow for some more accurate results. I'll just quickly mention that yes, the NFRC approach has this data with the exception of installed performance. It's just not publicly available to the design teams who need it. So that's potentially a gap that could more quickly be addressed. So at the end of the day, the obstacle really is they're not directly compatible standards. If you have data in one standard versus the other, it isn't a simple multiplication factor to compare the two. NFRC labels are really designed for standardized product comparison, which has a place in the market, whereas the passive house reports are really intended to help energy modeling and design teams model actual sized window performance. And so they really came at this problem with different purposes in mind. And so there really hasn't been a way to do one way versus the other using our tools in North America until now. This is where Peel Passive House and RDH came together to develop a therm procedure that outlines all of the requirements for modeling a window to the passive house standard, or not the most precise way of saying it, modeling a window using therm to produce outputs compatible with the passive house planning package. The full name is shown on the slide there. It's a bit of a mouthful, so I do just call it the reference procedure. It is available for download freely at fenbc.org. Link is below. It has example files, calculators, thanks to Peel Passive House, actually, who developed those calculators. And the procedure document is very similar to the therm manual for any simulators out there who are kind of curious for how they might get trained to do this. At the end of the day, the procedure is focused on really allowing manufacturers or design teams to simulate products to the passive house standard and allow for comparison to the NFRC approach. And so there's actually a template at the end that kind of lets you present both data points side by side with their respective metrics. But I guess need to stress as well that although the procedure has been recognized by recognized by the Passive House Institute, it is not the same as certification. So those are two different procedures. The reference procedure using therm doesn't replace the certification program by the Passive House Institute and would not get your product listed in that component database if that's what you're looking for. Nevertheless, we've had quite a bit of success locally using this procedure, and thanks to additional funding with our local governments here. So that kind of leads us to our policy discussion later in the symposium. And really, there are several really interesting success stories in our market due to this, not directly the procedure, but due to the incentives and policy strategies used here to provide design teams with local options for high-performing window products that are certified to the PASPO standard. So there's kind of a good news story there. And with that, I'll end.
Thank you so very much, Daniel. That was really a fabulous synthesis of the two programs. So what we're going to do now is flip to having a moderated discussion about the challenges that we presented and some of the conflicts and the disconnects between these two window certification protocols. But we've heard a lot about the differences, but I think what is often left off the discussion is, what are the real core similarities that we can highlight, and where do we see some alignments? Because I think in that alignment is where we can potentially find some real movement forward. So perhaps, Helen, I'm going to throw that question to you. I mean, where do you see some real opportunities for these two protocols to move together to synthesize, maybe not merge and harmonize, which I think is becoming the popular sort of phrase, and the initial attempt is to try and make these two things become one. Where do you think are some potential opportunities for each entity to sort of use elements of the other protocol to enhance their own programs?
Well, I think when you look at the pros and cons between the European and the US approaches, there are some pros to both. And, to be able to effectively calculate the edge conductivity and the frame conductivity and know what they are is certainly an advantage. And I think what Daniel just talked about, the ability to do these calculations in therm is a really big deal, because if you can't, if there's a requirement in European numbers, for example, and we don't work on the same scale or the same calculation method, it's really hard to design and compare to know whether you're even going to hit the target or not. So having our calculation tools capable of giving us numbers that align with the passive house standard is a really big step, because then we know we're actually looking at apples to apples, not apples to oranges. And that's the problem right now. I mean, we often see just a translation of units, even in central glass or whole fenestration assembly, and it's the wrong, you just can't compare. The numbers are just not right. So I think having the calculation methods there will be very important, and it shines a light then on the gaps and what needs to be closed. And me personally, I think on the spacer side, I would want to be sure that when we see spacer components listed, we're also making sure that they are associated with an appropriate sealant system, and as Adrian pointed out, the appropriate sealant height. We already see, even in our North American system, when we're using therm, the sealant heights aren't necessarily right when we're doing NFRC modeling. It's probably the same on the passive house side too.
So Adrian, I'm going to throw that question to you too. What are these opportunities, these crossover opportunities to really learn from each other's processes and protocols that you see?
Yeah, I think the first important thing is to be aware where the different procedures or methodologies come from, right? So, and when we look at the procedure we follow at PHI, for example, the idea behind the whole certification process was to be able to produce the values the planners really needed in order to predict a very high, or to get a very high accuracy, right? So, and also there was a kind of scientific approach which lies within the reason, how can we improve components, right? How can we get to the levels we actually need? And so therefore there's a certain necessity when we move in that field to have all the different components, or we can see what can we do to improve our buildings at the end. I didn't want to judge the different methodologies at all, but I think, yeah, as we've said before, the purpose was a little bit different. And when we look at the overall performance, the also kind of when we look at physical testings, right, measurements to simulations, that causes some differences, right? When we talk about aging of materials, when we talk about, yeah, what's happening after 10 years, things like that. So they are different, but I don't think that we can bring them together because they have different purposes, but they're both useful and helpful to, yeah, to get a better, yeah, better physics results, right? So, yeah.
Well, I think you've nailed the real end goal. I think we all share a common purpose of wanting better performance and better buildings. You know, and I think overall that's what we really need to continue to focus on. So Daniel, given that sort of context, you know, how often are you seeing manufacturers now utilizing this this protocol, and you know, what's the sort of process for that? Can you kind of give us a little bit more detail on how that works?
Yeah, sure. You know, I've seen actually one of our speakers kind of later in the symposium is gonna, you know, has direct experience with use of that protocol, and kind of their use case was, I've got a product, I think it's pretty good, I think it might be Passify certifiable, but you know, I want to make sure, I want to check before I go to PHI. And so the procedure was used simply to evaluate the design using the, you know, the other standard approach. So it was, you know, used to kind of, you know, validate it before seeking certification, because before you do that step, you just don't know. Is it worthwhile reaching out to PHI for certification? You know, you just don't know until you try. So that was one use case. Other use cases are when you have, you know, products which are somewhat limited in scope on a project, and you know, really availability might be quite small. So you know, exit doors for stairwells or entrance doors that are otherwise handled in somewhat a one-off basis that may not, you know, you may not have 1,000 of those on a job. You might just need to find a product that's available and fits. And so it's been modeled on a, you know, product specific basis for a project. And then just really kind of, there's nothing in North America really, well, until quite recently, really talking about installing a window and how do you model the installation, thermal bridges and that kind of thing. And so for the most part, you know, that's kind of where I think most people interact with it, is really to understand that component. But I will say that, you know, there is still, you know, from a manufacturer's perspective, a simplicity in the marketing to have the right label for the right project. That design teams who are on a Passify project have 1,000 to 1 things to worry about, from the length of ductwork and where you insulate and air admittance valves and everything in between. That picking a component that doesn't create any more hassle is just often where design teams end up. So that might answer your question.
Thanks, Daniel. No, I think it's an interesting conundrum, because I think, you know, what you've highlighted and what Helen highlighted too is we can go deep into the weeds on specific energy metrics, that ostensibly may not make a huge impact on the performance on one particular window. But if we extrapolate that out to multiple windows and on bigger buildings or even on smaller buildings, really understanding what the impact of your specific choices are is, I think, at the core of what we're trying to do in the Passive House community. So I'm going to switch topics a slight bit and sort of look at, dial back out, think about things other than just energy. We're all just hopefully coming out of a global pandemic, and health and comfort are really become a lot more elevated in the public consciousness. So the question I have for you on the panel here is, we really focus very intently on energy, and I'd like to hear from the panel, what are the other metrics that we should perhaps be really considering beyond just energy? And should we really be balancing energy with health, comfort, and even embodied carbon? Where are we going with that, and how are these frameworks looking at that? Why don't we start again with Helen, and then we'll go to Adrian, and then Daniel. I get your perspective on as the sort of mediator between the two of these at the moment. Helen.
Well, I mean, I think if we think about what's happening in North America and what drives window performance, it's really thermal. And, our codes don't talk about condensation. In fact, they specifically don't talk about that. They're not talking about indoor air quality. I mean, of course, we have some above code programs like LEED and IGCC and ASHRAE 189.1 that get into those areas, but those are very small proportions of what we do. That was one of the things I like about the European approach, where you have a much better balanced design by nature out of the fenestration design. Whereas in the US, you end up with driving all the thermal through the center of glass, and you end up with condensation issues because you've forgotten about the frame and the edge. I'd like to think that there is more of a trend that's going to move towards comfort and condensation, even if it is just through, for example, thermal bridging being taken into account. I know thermal bridging is coming. Hopefully there will be some language in it for the next ASHRAE 90.1 standard. We're working on something for IECC 2024. But that's another great thing about Passive House standard, where they really care about thermal performance and condensation, and it's really wrapped up into the whole standard. So we could do with a more balanced approach in just general North American codes and standards.
Great. Adrian, I know you've got a lot more to say about health and comfort.
Yeah, I think that, well, the Passive House concept itself is a purely functional concept, right? So, and it requires a certain efficiency from a thermal perspective, that's for sure. But the main goal is to have the highest comfort, the healthy environment, the best hygienic levels, right, in terms of, preventing mold growth, condensate on surfaces and so on. And also, when we look at embodied carbon and all these other aspects. And if you follow these guidelines and all our criteria, they're based on comfort, right? Then efficiency or the thermal perspective is the natural way to go. So
they're good allies, right?
Yeah. So I think we always think of, well, what can we do to live in a healthy environment? And then the next step will be just what components do we need, right? And this is the question we ask ourselves all the time, and this is how we develop the criteria. But I think that I've thought about that when I've seen Daniel's presentation, that this is the thing we need to talk about more, is like synergistic effects, right? So when we talk about the design aspect, when we talk about incorporation of different components, incorporation of HVAC components, how can we combine this? How can we, this is the next thing to develop further.
Thanks, Adrian. Daniel, any thoughts on all those additional,
many thoughts, but
Great.
the short answer to your question is yes. Now, the long answer to the question, I'm going to answer in 3 stories that are sort of pro passive house, and then one that's kind of con passive house. Story number 1, we're looking at building energy retrofits of some existing buildings in Vancouver. They're roughly 6-year-old buildings. They were designed with regular glazing using NFRC labels at the time, and the window was put into the building. And one of the major findings of this particular study, monitoring study, was that these buildings are experiencing massive overheating. There is insufficient, inadequate ventilation. The window was a component, but it also served a critical design element in these buildings. It was how they get fresh air. So when you don't know where it is and how that can perform from natural ventilation perspective, you've kind of failed and missed an opportunity to improve air quality. So if you're relying on your window for ventilation, you better know where it is in your project and how effective that is at natural ventilation. And this is something that the passive house planning package and the approach really lets designers understand. So knowing that your window opens is not something that is typically looked at in much detail when you assign a U value to an area on a project. So that's somewhere where I think one approach versus the other does a bit better job of understanding the other purposes of a window. The other story that I'll give is I grew up in Ottawa, which is in Canada, the capital, probably one of the coldest capitals in the world. Had double glazed windows and saw condensation every winter. I didn't care. Now, this happened around the edge of glass, has sort of older spacer technology, and somewhat along this line, NFRC has condensation indexes. They have ways of assessing condensation risk, and they intentionally ignore edge of glass. And there are a couple of reasons for this. I won't go into those in very much detail, but they ignore that area. One thing that passive house does interesting is they don't ignore any part of that window. They put it into the wall and they figure out if there's a condensation risk introduced because of installation. And then one step further is they're not just concerned with liquid water on the window. The threshold for condensation risk is actually lower. It's actually a surface humidity of about 80%. You're controlling for that mold and mildew growth that I had to wipe off the window edge every summer. So there is kind of a fundamental difference in how they're thinking about temperatures on that window product, namely not ignoring parts of the window and being more conservative in terms of what they're controlling for. All right, now I said there's going to be a bad story of passive house. Here's the bad story of passive house. And I'll say that it is being fixed as designers get more experience. So the key number in passive house, I forget the inch-pound unit, is 15 watts or kilowatt hours per square meter per year. That 15 number is the North Star of your passive house project. And what that means is designers, when they need to reduce that number, is they let in more solar heat gains. Not a problem if you control it when you don't want it. Now imagine that this, in a hypothetical building that may or may not have happened in real life, your shading relied on a tree. And hypothetically, the contractor cut down this tree. Then you've lost your control of solar heat gains, and suddenly you are potentially resulting in extreme levels of overheating and discomfort. So when you are making decisions to decrease your, what they call the TEDI number, or the heating demand intensity, and you're relying on your windows as part of that solution, just pay attention to how you're controlling it. And there are scenarios where that's been done poorly. So windows are super complex. They do a lot in a very small package, and choosing a standard and design that anticipates those is quite important.
That's a great point, Daniel. I think, a lot of us in our early passive house modelings made that mistake of trying to do passive solar instead of doing passive house. And I think it's a lesson very well, worth learning, and hopefully not too many people learning it the hard way. So switching up a little bit more again, I'm going to go back to a question that, as a practitioner, I am always asking. Here we talked a little bit, and I showed this in the slide that I shared at the introduction, that for our regulatory submittal requirements, we are required to just share our U window value, which is the NFRC, why the NFRC has developed that. It's really evolved as a protocol in collaboration and in connection with most of the code regulatory frameworks that exist here in the US. And as the passive house community has grown here in North America, we are having this disconnect because clearly we need a lot more granular information. And where it presents challenges is it sort of limits the number of product choices that I can source from that have that data available. So the question I have for you guys, if you had your wish, all of you, could we structure each of these programs to perhaps become more inclusive, and offer more transparency and more data? And how difficult would that be? Because really, from a practitioner's perspective, it shouldn't be that hard. So I'm just wondering if there are things that I'm missing here, and I'll start with you, Helen, to see, if you have any thoughts on that, and how do we add transparency and inclusion into the window industry here?
So when you say transparency, you mean in terms of what gets labeled, what information gets labeled?
Yes.
So
that more granular detail that we know is available, it's there.
Right.
It just doesn't get daylighted, right?
Right.
How do we get that to happen?
I mean, ideally, if I had a magic wand, right? I mean, then you'd probably want to change your NFRC label to have more detail on it. So you have your overall U factor, you have your overall SHGC, and then maybe if we want to have transparency for those passive house practitioners, you'd have the frame U factor, you'd have the edge of glass U factor, and you'd have the center of glass U factor. I have tried, and in all disclosure, I'm now a new member of the NFRC board, but I'm also have been actively involved in NFRC for a while. I have tried to get Spacer Systems edge of glass ratings at NFRC, but got a lot of pushback because they say we just rate assemblies, we don't rate components. So that's the pushback I got. But if I had my magic wand wave wish, I would suggest having those available either on the label or just as a secondary source of information that would be easily available. Which, I mean, you can get that information from Therm. I'm sure, Daniel, you tell me you can pull it out, right? It's there in the calculation method.
Yes,
Yeah,
it is.
no, that's kind of the irony of all of this, right?
I appreciate your use of the word transparency in the context of window information. But yeah, I think I agree with Helen really that they're not so fundamentally opposed. I think it's still a 2D simulation. It's still a window cross section. Passivhaus takes a few more steps just to kind of understand it in the context of the building, which I think we can sort of handle outside of labels, to be honest, because it's done on a project basis regardless. Um, Although I would encourage manufacturers to consider it, because you'll notice that there are certain features of products that are successful on Passivhaus projects that you'd miss if you didn't think about it. But yeah, I think I agree. I would very much like to see more information available. And actually, someone in the chat also mentioned that basically you don't have any option of getting this information from most manufacturers. I think if the therm files were listed in the NFRC certified product directory, that would be awesome. That means teams could run with it. They could model it installed. They could pull the edge of glass value. They could swap spacers. They could handle all this sort of outside of that labeling program. From NFRC's perspective, if you look at some products, there are entries with over 1,000 different options, all for different glass types. It is a monstrous, like it's so precise in terms of kind of all the different pieces that go together. And there are some very, particular rules to create a certified record, that it is a monstrous data problem. And that there are some simplifications that, have an impact on accuracy following the Passivhaus approach to generating a UF number versus a psi value versus a glass value, because they are treated separately. You don't necessarily get all of those combinations and permutations that you would in NFRC. So really, it'd be kind of a really fundamental shift in the two approaches to get them to align that I don't think we'll see. But more transparency in terms of the files and data would be awesome.
Thanks, Daniel. And Adrian, maybe I'll shift this question slightly for you, because I think, as a global institute, you get to see probably the same challenge everywhere, right? In every country that has a different fenestration rating protocol. So maybe you can give us some perspective of like what this looks like in other countries and how this has evolved and shifted in elsewhere.
Yeah, I think this is an issue which is not only applicable to the fenestration, right? This is also applicable to the treatment of conductivities for insulation materials, for example, right? I just would like to add some things. So when we have very huge buildings and a lot of different window components, usually it's the case that these are repeating details. So once you have, you inserted the 20 values you are going to need, you can copy and paste, right? That's usually the case. It's not like there's a high rise which has a completely different setup of windows on each story or something, right? So usually the additional work is manageable. I've read in the chat a couple of things. But okay, maybe let's stick to the question first. It's always complicated when there are a lot of different methodologies going on. And for example, in Europe, we got this CE branding. All the manufacturers, they need, in order to sell the products, they need to have the evaluation of the thermal performance, and also from the driving range security and how you get fire resistance and everything else, right? So, and these are sometimes also different tests. So, and when you ask a manufacturer to provide the details, I got like, how you call it, a nightmare cabinet of something of thermal bridge calculations. So usually you don't get reliable values, right? So, as long as they don't have this CE branding. So, we can really hope that we can only educate and try to make use of databases, right? So you can also make like these cross comparison, right? So is my connection better than the one I've seen certified on this certificate or something? I think procedures like the British Columbia procedure to evaluate window frames is a good step to, yeah, also to educate, right? For the planners to get a better feeling for these simulations. Apart from that, it's really tough to compare results, especially when there are hotbox tests or physical tests compared to simulations. Also, simulation boundary conditions really differ. Yeah, so that's a problem. Yeah, but yeah, when we don't know the exact values, we try to start with conservative assumptions, and in case it doesn't work out, we look at that in detail. But yeah, that's it.
Thank you, Adrian. So Helen, you raised you touched on a subject that I think is really an interesting opportunity for the passive house community to really assist conventional code frameworks to move the market forward. And that's with thermal bridge calculations, which in the passive house community have become a requirement, and it's really expanded the language and the capacity of our North American community to even, first of all, understand what those are, because before I did passive house, I had no idea what a thermal bridge calculation was. To expand the number of professionals who can even do thermal bridge calculations, and I was, in my early career, I had to teach myself how to do therm because I had to understand what a thermal bridge was. And I know I've spoken to LBNL, and they've told me that the global passive house community is one of the larger users of therm. So, this is an opportunity that I know I'll speak about in the second session a little bit more, but as the IECC starts to look at including thermal bridging, and because passive house people know, first of all, what that is, and secondly, how to do that, how do you see that? Do you see potential for these sort of merging a little bit more and using passive house as a front runner to build industry capacity? And love to hear your thoughts on that.
Daniel, do you want to go first? You probably have most experience. I'm just at the code end of it, as opposed to the practitioner end.
It's going to be interesting because as you move towards higher performing buildings, I think there's some performance-based standards like passive house that are driving that. When you actually care about heat flow through a building and you want it to be very, very small, then the amount of heat loss through thermal bridging becomes a really, really important deal. You can't have 15 kilowatt hours of loss through thermal bridges if your target's 15, which does lead to some interesting conversations about some what would commonly be referred to as silly detailing, at least from the contractor's perspective of things we're asking them to do. So I think that's going to be interesting. And the reality is the goal is to make buildings more efficient, and you're overnight going to see them 30, 40, 50% worse, simply by changing what we're accounting for and requiring that, which is going to really just make minds explode in terms of, there are 20 enclosure is now R5. Okay, how do you understand that in your building context? And I can explain that to the owner, the clients, the designers. So super interesting from a code perspective.
Yeah, and I think that's why we're having some challenges right now. So I'm on the envelope subcommittee for IECC 2024, and I'm working with a group of people. I represent Facade Tectonics on that. We're trying to take a first step to introduce even the concept of thermal bridging into IECC to represent what's going on, not necessarily to move the needle a lot, but just to at least represent what's going on in current standard practice, because at the moment we assume all our interfaces are perfect, right? So, and when you're trying to do a great passive house, right, and you're dealing with all the thermal bridges, when you model that in IECC and then you compare it to the baseline, well, the baseline's perfect, but of course, even the passive house isn't necessarily perfect. So your passive house looks worse than your baseline building, which is crazy. So we have to at least take some certain steps, but I don't know that we all need to be great at doing thermal bridge calculations, because I think the thermal bridging guide is a great first step to getting us there without having to calculate psi values. I mean, you can just go look up a standard interface detail or assembly detail and go, okay, that's mine. I'm going to use that. It's got all the numbers there. I'm good to go. So I think that's a good first step. And Daniel, I'm sure you're more familiar with it and have used it
extensively. And I
Well, I
agree
think-
that guide's a good first
Yeah.
step.
No, I think you're raising the point, Helen, that, you know, I think what we're seeing as from the practitioner level is just even knowing what that is and learning, you know, incorporating the habit of actually referencing that and understanding it, you know, and seeing what the impact of that is in your building. Because you know, as I said, it's an area that I had absolutely no understanding of as a practitioner until I took passive house training, and you know, that's been a real eye-opener. Here in California, I know the codes and standards teams also looked at how can we incorporate thermal bridge calculations into the energy modeling, and my understanding is they found there's just not enough expertise on the ground at the moment to even consider adding it. So
we the Facade Tectonics Institute put in a proposal for this cycle to get them to think about putting that in, because I think with the thermal bridging guide we have at least a baseline to use without having a huge number of people that can do psi value calculations. And the proposal we're working on at IECC has a prescriptive guide, a prescriptive requirement. Again, this is just a proposal, but it basically has some prescriptive guide to the 5 main thermal bridge areas, like the attachment of fenestration being one of them. That doesn't, again, require you to have a psi value calculation unless you want to do that.
Great. And Adrian, you can perhaps speak to some of the resources that PHI has made available. You want to share those?
Yeah, I think, first of all, I would like just to mention that in 95% of the cases, you don't need to simulate or calculate the thermal bridges, right? So all these purely geometrical thermal bridges and also a lot of constructed thermal bridges, you can find them in catalogs. And even if you have a certain experience and you know that this is not the worst idea how to install a window or whatever, you can make a conservative assumption and see if it works out. And at the end, and therefore we have a kind of good planning tool which shows you or gives you an indication where are the highest losses or gains or whatever. And then you can look at this particular detail. So usually, if it's not like a hospital or swimming pool, we usually just look at very specific details. And then it becomes a little bit more tricky when we talk about dynamic or transient thermal bridges, right? Everything where we have like a fluid running or something. I don't want to cover that right now. Yeah, so there are a lot of catalogs available also on Passipedia, and yeah, a lot of manufacturers provide them for purely geometrical, and that's a good start. And also for sure the building system certified building systems, we are trying to publish more and more full reports, also from things we did in the past. So for each certified system, we are going to provide a thermal bridge catalog in the future. So this could help a little bit. But nevertheless, I think it's important to get a basic understanding of what's going on here, right? So you can work with catalogs, but everybody should be able to at least conduct a simulation for a geometrical thermal bridge, not for windows or something, or facade anchors or whatever you do. But I think it's the basic principles. It's a good task, and you can learn it within a day or something. I think this is a there's so many free tools to use. Yeah, Therm is not that popular here in Europe, so nobody's really working with that here. But I think it's for free, right? So
It is a free program, and it's government funded and developed right here in California, up the hill in Berkeley. So yeah, and just shameless plug, the Passive House Network does provide training for how to use Therm. So for people who want to actually just dig in there and actually get a handle on that, that's a great place to start. So Daniel, maybe you can also, you work directly at the interface of both these, the certification protocols and the implementation in the field with real buildings and real practitioners actually trying to build high performance buildings. What are you seeing the bigger challenges with regards to windows specifically, and maybe installation of those products, fenestration? Where where do you see opportunities that could
Step one,
could do with shift?
design. It's not even modeling related. It is simply that North American teams just do not count for the perimeter interface. So getting that information requires someone that you don't really like very much looking at the drawings and pulling that number off the drawings. Simply so you have a quantity. And it could be kilometers of this quantity. So even small numbers, even if you're guessing at it, getting that initial quantity to assess it is actually an incredible challenge on most of our projects. Although we're kind of getting into the habit here, at least in BC. So it's not super technical. It's simply counting. It was my very first co-op job, was doing just counting, but that piece is actually quite challenging. The next thing is just, really goes to window positions. So it's hard to stress how important that is, but as you move your window in and out of a rough opening, especially in the context of super insulated thick walls, you impact shading, you impact the attachment mechanism, you impact the thermal bridging at the end of the day through that window. And that's something which can change your thermal bridge value, orders of magnitude, from thermal bridge free to super thermal bridgy, and taking your triple to a double glaze performance. So getting that right is really important, and does result in sort of membrane challenges, attachment challenges, and other things that designers of the who's drawing that detail in may not fully appreciate.
Interesting. And I think, as a practitioner, that's really has been a huge, big learning curve for myself. Just, the implementation and the installation. I never realized what a massive impact that could have on the building performance. So we're coming up to the hour. I would like to, wrap up so that we can have our break. I think this has been a super interesting discussion. We've really identified some of the challenges, the disconnect, the apples and oranges between the two methodologies. I think we've underlined the fact that you really can't compare them directly. They're just not the same thing. But we've seen the challenges, the benefits, and the strengths of each of them. And I really appreciate you guys sharing the both the benefits and the challenges. I think it's very important for us to really daylight all this, and so we can hopefully move things forward a little further. 2 seconds, anybody want to do some closing comments before we go to the break? And I'll start with Helen, Adrian, and then Daniel before we sign off for a short break.
Thanks, everybody. I would just say devil's in the details. Got to have a balanced approach, got to have the thermal performance, but you can't compromise the lifetime. Otherwise, you don't have good thermal performance.
Thanks, Adrian.
Yeah, I think your question was in the beginning, what can we do to be more inclusive, right? I think we can also try to be less exclusive. And so we have to appreciate the different methodologies, although they have a slightly different purpose. And I don't see the actual necessity to convert them into one, thing. So we can live in peace together, right? With two different methodologies to evaluate window performance. I don't think we should consider as like, these are opponents or something. So yeah, that's mainly it. So let's all live in peace.
Wonderful. Thanks, Adrian and Daniel. I get you the closing comments here.
It was super important.
Session.
Design for a purpose. Just know why you're doing it. It doesn't really, from my perspective, physics doesn't really change across the pond. Just know why you're doing it and use, there are tools out there to help you with that, whether it's heat gains, U values, structural support. Just remember why.
Fantastic. Thank you. I think that's closing with just more information and know what you're doing, get the knowledge. All right. Well, thanks, everybody. We're going to take a break now. We'll be back in 10 minutes. So I look forward to continuing the discussion and digging into the policy section. Thank you.